Hello, and you can see I've got another hat on today. Not sure it shows up very well against the writing. Anyway, let's crack on then. So let's share my screen. Okay, move that out of the way. Okay, so we are now looking at 24.2 complex ions and their shapes, and what on earth is a complex ion? Obviously, we live to help you and to help you do as well as you can. Okay, so what are the catalysts in these reactions here? So we looked at these last time. Okay, catalysts in the hydrogenation of ethene to make ethane, the Haber process, contact process, catalytic converter. What are the catalysts in those? Do you remember what those are? Okay, so let's go through what they are. If I can get this to work. There we go. That might help. Okay, so nickel, yeah, and you hopefully should start to remember that from the organic chemistry and the organic syntheses, that nickel is one of the ones we can use for hydrogenation. Iron, hopefully you remember that iron is the Haber process. Vanadium pentoxide, which we did last time, is the one for the contact process, which produces SO3, which is going to be important for making sulfuric acid. And then finally, we've got a catalytic converter. Okay, and that will be a mixture of platinum, palladium, and rhodium, which probably explains why they're obviously quite expensive metals. The catalytic converters are sometimes stolen from the bottom of cars. So are they homogeneous or heterogeneous? They're all heterogeneous. They're all of the case where the compounds that are reacting come down to the surface, stick to the surface of the nickel or the iron or the vanadium pentoxide powder, and then that enables the correct orientation of the reacting molecules, and it also reduces some of the energy. So, for instance, if I can just draw this very quickly. So here is my surface, which might be my nickel catalyst. Okay, so my nickel catalyst. So actually, no, let's do the Haber process easier. So we've got our iron here. So this is Fe, the surface of the iron. Okay, and we might get our nitrogen come along, okay, and it sticks to the surface, okay, and it sticks there. Now in doing so, it's going to weaken the bonds here. So when H2 comes along, okay, we can start to get some reactions happening and getting the formation eventually of ammonia. Okay, let's see if we can get rid of that. I'll just move on. Yeah. Okay, so this is our aim today, to look at the idea of a complex ion. This says quite a few new terms here. So we've got complex ion, coordination number, dative covalence you should be aware of, and we have these complexes, which are complex ions, and they tend to have six-fold coordination with an octahedral shape. Some will have four-fold, which is square planar. And there are some examples where we just have two-fold coordination with a linear shape. Okay, so this is in the textbook, pages 141 to 144. Obviously, please read that and make sure you're au fait with it before the lesson. So we've got a complex ion. So definition of a complex ion: transition metal bonded to one or more ligands by coordinate bond. There's a new word there, ligands as well, by coordinate bonds or dative covalent bonds. So it's a covalent bond. Okay, so we're getting a metal that makes a covalent bond, and the covalent bond is formed because the ligand, which is what is binding to it, could be something like water, has got lone pairs of electrons which it can donate to make a coordinate bond. Okay, so a ligand, a molecule or ion that can donate a pair of electrons with a transition metal to form a coordinate bond. Okay. And remember that covalent bonds are just covalent bonds. We call them dative covalent or coordinate bonds just because it's for us to understand that the electrons have come from one of the atoms only, not two in the bond or the ion. So coordination is the total number of coordinate bonds formed. Okay, so for instance, if I've got copper 2+, I can get a coordination number of 6. I can get 6 water molecules to surround copper. Okay. So the ligands, to be a ligand, you need a lone pair to donate to form a bond. You're going to get a coordinate or dative covalent bond. The number of coordinate bonds is called the coordination number. That's fine. What ligands could we have? Well, I've mentioned one already, water. Okay, so here are a few others. So we've got water, we've got ammonia, it's got a lone pair. We've got oxide, they've got obviously got lone pairs. OH-'s got a lone pair. Thiocyanate has got a lone pair. Now, what we will have is some new nomenclature. Okay, we've got some new nomenclature coming in. So, you're probably aware that in an organic molecule, if we've got chlorine in it, we call it chloro. Now, cyanide, we call cyano. Thiocyanate is thiocyano. Okay, if we've got water, hydroxide, that's hydroxo. Oxide is oxo. That you also come across that when we've got aldehydes and ketones. Okay, but the aldehyde or ketone is not the main functional group. We call it oxo. Water, aqua, obviously that makes sense. And ammonia we call amine. Okay, and amine, now note the difference. This has got 2 M's in it, not 1. So an amine is something different. An amine is NH2 joined to a carbon compound by a covalent bond. This is the ammonia itself stays as ammonia, and it has a lone pair, and that lone pair will form a dated bond, okay, to something. Okay, let's get rid of my no, I didn't actually get rid of it, did I? Oh, hang on, wait, pointer options. Let's get rid of the pointer. Right. Okay. So they're all monodentate or unidentate ligands. What do you reckon that means? Mono, dentate, teeth. Okay, so dent comes from teeth. So it's like teeth. It's like the lone pair from this ligand is going to bite into the metal. Yeah. So monodentate. It can only make 1 bond. Okay. So ammonia, water, oxo, they can only donate 1 pair of electrons to the central metal ion to form a coordinate bond. And so let's hear more about ligands. So 1 pair examples. Okay, so form 1 coordinate bond. You can see the lone pairs down in the diagrams. Okay, right. What do you reckon you call it if you had a ligand with 2 binding sites, 2 lone pairs on different atoms? They'd have to be on different atoms, otherwise they wouldn't be able to get round the metal. They need to be separated. Guess what? If it's got 2, it's going to be bidentate. Okay, so we've got 2 coordinate bonds. We can have multidentate and bidentate ligands, and they will get more stable complexes. So I could have water, which is monodentate, but I could replace it with something that could be bidentate, and the bidentate one wins out. Why? Okay, let's have a look. So we've got some examples of bidentate ligands. Okay, so we've got diamino ethane, yeah, okay, diaminoethane, or sometimes it's called EN for short. Okay, so when we're trying to speed up our writing of stuff down, we might just call this N. It's got 2 amine groups on it. Okay, so diaminoethane, or amino aminoethylamine, yeah. There's a lone pair here, a lone pair here. They're separated by the 2 carbon atoms here. So that means they could come around a transition metal to form the complex. Now we've got oxo, which is ethane dioate, yeah, okay, which is like got lots of oxygens in it, yeah, and we've got a lone pair on this oxygen, a lone pair on this one. Imagine this has come from ethane dioic acid, and it's lost its hydrogen on both carboxyl groups. And so we've got these lone pairs. These lone pairs can then stick to the transition metals. Okay, so what we could have here, okay, is the N, yeah, so, or, diaminoethane, and it has got a covalent bond here to cobalt, a covalent bond here to cobalt. That's 1 molecule of N here. Okay, actually I will just draw that. So that's 1 molecule of N. Okay, that's another molecule of N. Okay, and that's a 3rd molecule of N. It's bidentate. Okay, so it can join with this nitrogen and it wraps itself around cobalt. And if I have 3 of them, I end up making this octahedral complex with 6 covalent bonds joined to the cobalt. Okay, and up here it says the charge. This is cobalt. I think it probably says 2+, could be 3+. I'm trying to work it out. It's been rubbed out. But what happens though, because this does not have a charge, and this is a metal ion, the overall complex still has the same charge that this ion started with in the first place, and you'll see that in a bit. Okay, so here is the ox acting as a bidentate ligand, again wrapping itself around in a similar fashion to the diamino ethylamine, or diaminoethane. Yeah, it's wrapping itself around in a similar way to give us a coordination number of 6. There's 6 joins to the cobalt, and there's 6 joins to the cobalt here. Okay, now if we look at the equations, right, which is more likely in terms of entropy? Well, how many molecules have we got here? We've got 1 complex ion molecule, and we've got 3, okay, diaminoethanes. Yeah, so it's 3 of those. On the right-hand side, however, we've got 1 complex ion, but we've got 6 molecules. So we've gone from 4 molecules to 7 molecules. So we've increased the entropy because we've got more molecules. We can spread the energy out more, and that's good. We've increased entropy. So we can explain why this is more stable than that, because we increase entropy when we make this. Okay, and the same thing goes when we have the cobalt. So actually it is 2+. That's 2+ up here. We'll just see that. You can see that in the equation. So the cobalt was 2+. The En or N, 3 molecules of N have surrounded it. Okay, and it's still 2+ because the En, or the diaminoethane, has no charge of its own. So the complex stays as 2+. Notice how we've written it. We've written cobalt brackets H2O brackets 6, because there's 6 of would be 6 of them surrounding it, in square brackets, followed by whatever the charge is, which is the cobalt. Okay, now the thing is, we have said that some ligands could be negative. So for instance, I could put chloride with this, and that would change the charge here, the overall charge of the ion. Okay, so we've got our complex. We've got the idea that a bidentate is more stable than a monodentate. That's monodentate. That's bidentate. It's more stable because we've got more molecules in our product side, and entropy favors that. So let's have a look at this. Now, there are some other words. I'm sorry. We just have lots of words for different things. Chelate. Okay, chelate comes from Greek meaning crab claw. I'm just going to try and stop this chair to make sure it doesn't creak. Try and sit still. Okay, so chelate, yeah, is Greek from crab's claw. Okay, so you can imagine that the ligands are grabbing onto the metal ions. So this is Cu2+, okay, and it will grab on. Okay, the first example is all unidentate and monodentate. Second is chelated. Chelated ones, okay, contain di and multidentate ligands. Okay, so if it doesn't have multiple, or it's not a ligand that can do not bidentate or multiple dentate ligand, then it's not chelation. Chelation it would help to remove certain ions from systems, so we can use it to help clean things up. So so chelate, yeah, crab's claw. Obviously, the En, or the diaminoethane, is like a crab's claw. It's got 2 points, whereas water is not like a crab's claw. It cannot grab it. So, if you remember that, you'll know that this is chelate. This is a chelated one. And actually, what's quite interesting here is that this one has got the En here, and it's got water. So it's got, we could have some really quite complicated names, couldn't we? We'll look at those in a bit. Chelated ones are more stable, yeah? Increase in entropy, remember what I said, yeah? Okay, so here I've got 1, 2 molecules. Here I've got 1, 2, 3 molecules. So this is much more favored because it's more entropy. And notice in this one, I've got 4 aquas and 2 amines. So, what could I name that? Well, let's call it diamine. Okay. Oh God, quatra aqua copper. Okay. and it ends up being 2+. So that's this one here. Okay, no, it isn't. That's the one with the En on it. But this one here, it's still 2+ because none of these have got charges on. So chelation, right? So coordination. This is in the booklet, page 25. The complex shape depends on the number of bonds around the metal. So a change of ligand will affect the number. So let's have a look at, think about something like chloride, okay? So I could have water, okay? And if I have water, I can get 6 water molecules around a copper or a cobalt ion. But chloride is a much bigger ligand, yeah, because chloride is a much bigger atom. And that means that there's less can fit around the ion. Okay, and certain things, certain transition metals, and you just have to learn this. There isn't sort of much rhyme or reason with it. Yeah, I prefer to have certain coordination numbers. So platinum likes to be square planar. So that means it's in the middle with 4 ligands surrounding it, or 4, 1. Well, let's not say, I can't remember the 4, tetradentate, that's the one. 4 tetradentate, one tetradentate ligand, i.e. that's one that's got 4 bits that can grab it, could surround platinum, or I could have 4 waters around it. Silver is linear, so it only has a coordination number of 2. So let's have a look at this. So let's go for some examples. So this is coordination number 6. The shape is octahedral. We've got 6 dative bonds, covalent bonds, joining water with its lone pairs to copper. And we would call that hexa aqua copper, okay? Or hexa aqua copper 2+, yeah? Or in fact, hexa aqua copper 2 with the 2 in Roman numerals in brackets. And you can see that it's a 2+ charge, and the ion stays as 2+ because water has got no charge. Okay, now let's have a look at this one. Ooh, got a 2- one. Okay, this is tetrahedral shape. It's copper. It's tetrachlorocopper. Yeah, tetrachlorocopper. We've got 4 coppers, tetra, and 4 chlorines, tetra, and so it's tetrachlorocopper. And it's 2-. It's 2- because the copper is 2+. There's 1 2+, but each chloride is 1-. So we've got 4 minuses. 2+, so overall it's 2-. Okay, notice how we write it out in its formula, yeah, with square brackets. Okay, right, square planar, we've got platinum. Right, so what we're going to call this, we've got diamine dichloroplatinum. Okay, and in this case the platinum has no charge, and so the complex has no charge, and so the coordination number there is 4. Okay, that one likes to be square planar as opposed to tetrahedral. Yeah, so yeah, some of these you just have to be aware of. Okay, and learn. And linear, here we've got diamine silver, or diamine silver. Diamine silver to silver plus. So the bond angles in that one, all the angles are 90. In that one, they're 109.5. We know that. In that one, they're all 90, and in that one, they're 180. Okay, so we can think about the bond angles in these complexes too. So chloride, why does chloride be tetrahedral, not octahedral? Well, this sort of diagram hopefully helps you to see that. Okay, so chloride ions are pretty massive. Okay, water molecules are not so massive, and so you can see the comparison there. So obviously chloride and water. Okay. So we would need to draw them in 3D. So we could draw them something like this. Okay, so here is iron. It's got 4 bromides or bromos with it. Okay, and 2 chloros. Okay, so we would call this tetrabromo dichloro iron. Okay, and the charge on this is 4-. Okay, well, okay, what does that mean? The iron must be 2+, because we've got 6 minuses surrounding it, Br minus, Br minus, Br minus, Br minus, Cl minus, Cl minus. That's 6-. The iron must be 2+ in here. Can you think of any other things that might contain iron in their center and have a complex? You get it. You got it. Hemoglobin. Hemoglobin is a complex ion. So what we've done to draw this in 3D is we've got our bold wedges coming, let's say, coming out of the screen. Okay, so they're coming out of the screen towards you. The ones that are dashed are going behind the screen, away from you. And the two chlorides here, or two chloros, are in the same plane as the screen. Okay, so we're using our wedgie idea to draw out our 3D structures. Okay, yeah, that's what I just explained. Square brackets, overall charge, very important. Okay, what is going on in this one? What's also quite important? Thing is, you're making covalent bond. A covalent bond is just a sigma bond, single covalent bond. It's a sigma bond, okay, with orbital overlap, and the orbitals have got these lone pairs in them, okay. But what we have done here is we have shown the arrow to show, well, and also obviously the lone pairs come from the oxygen. Okay, so that's quite good to actually draw the lone pair on to show it's coming in. And obviously we can draw the bond as an arrow pointing towards the ion, because the ion isn't supplying any electrons. The electrons are just coming from oxygen, or from the oxygen in the water. And because the transition metals, yeah, go back to the last presentation, have got unfilled d orbitals, we can stick electrons in there, okay, from to make covalent bonds from our ligands. Okay, now hopefully you should now be able to draw hexa amine cobalt 3+, okay, or hexaamine cobalt 3. Okay, so have a go at drawing that, and obviously continue when you have done it. Okay, it should have drawn it something looking a bit like that. I mean, you don't have to put the arrows on. I suppose it would be nice to show the lone pairs, but I mean, that works, okay, unless obviously I ask you to draw lone pairs. So complex ions, okay, so we have got these ones. So when do you need square brackets? So, well, you need square brackets when you've got an ion, okay, because the platinum does not have an ion, okay. So this one, yeah, has no brackets, okay, because it's not an ion, okay, it's just a platinum atom, okay. When do you need round brackets? Well, we've got multiple versions of polyatomic species, yeah, so obviously NH3 is a polyatomic species, chloro is not, or chloride is not, so we don't need a round square brackets there. Where does the overall charge come from? Okay, well, this one comes from the fact that silver is positive. This one comes from the fact that copper is 2+, but the chloride is 2-. So 4 lots of minus plus +2 gives us 2-. Okay, what's the oxidation state of each metal in the above complexes? So +2, +2, platinum solid, 0, and +1. Okay. Right, now another quite important chelating agent, or multidentate ligand, is called EDTA, which is short for ethylene diamine tetraacetic acid. Okay, tetraacetic acid. Let's have a look at this. Multidentate, forms several coordinate bonds. Okay, yeah, I'm not going to tell you any jokes about EDTA because they're just far too complex. Nah, not a good joke. Well, actually, it's quite good. Right, so this is tetraacetic. Okay, so we've got an acetic acid group here. We've got an acetic acid group here. We've got an acetic acid group here. And we've got an acetic acid group here. Okay, ethylene diamine. Well, that's an amine group here. And that's an amine group here. And that's got a lone pair. That's got a lone pair. These hydrogens can fall off to leave us with an oxygen, which is O-. So we've got 4 of those. So in fact, this has got not 2 crab claws, I can't do 4 crab claws, not 4 crab claws, but it's actually got 6 lone pair points. It's going to have a lone pair here. It's going to have a lone pair here, and here, and here, especially once that hydrogen falls off. Okay, or those hydrogens fall off, and it's got the lone pairs on the nitrogen, so it's actually got 6 points of attachment. So we can get the ammonia. Oh, let me get rid of that horrible for interruptions. Let's go for an eraser. So let's get rid of that. Get rid of that because they're in the way. And that one, and that one, and that one, and that one. Okay, I'll leave the lone pairs on. That's fine. Okay, and let's get just automatic. Okay, so back to without pen. So you can see that the lone pairs on this oxygen, they combine to the metal. There'll be a lone pair on these nitrogens, they can combine, can join, and the lone pairs here can join. By the way, what type of a structure is this? Yes, that's right. It's a di-substituted amine. So it's N, N, something. Okay, we've got a group, not a hydrogen on here, not a hydrogen on here. If this was an H2, it would just be a primary amine. But here we've got well, it's a tertiary amine there, isn't it? Okay, because we've got not one but 3 groups on it. Okay, so EDTA is actually going to be -4 in charge because we've lost the hydrogens. So 1, 2, 3, 4 hydrogens lost. We've got O minus here, O minus here, O minus here, O minus here. So it's -4, well, 4 minus in terms of charge. So reaction here, okay, this is going to be a very strong complex over here because what we've done is we've gone from 2 molecules to 7 molecules. Much more entropy here. This is much more stable because I've got more, I've made more entropy because I've got 7 molecules rather than 2 molecules. So we could get that happening. Okay, it's an important complexing agent or chelating agent. It's used in detergents. We can bind up calcium and magnesium. In foods, it's a stabilizer. It removes any metal. It can be reused to remove metal ions. Prevents clotting of blood. Okay, so it's a pretty decent thing. Okay, so metal complexes in biology. Heme, the heme group. Okay, it's got iron in it, iron 2, which gives the red color of the blood. Okay, so what happens here? This is the heme group. This is the heme group. It's a chelating complex, and it surrounds the iron. And we've got 4 nitrogens, which have got lone pairs on. Basically, that's an amine group. There is an amine. Lone pairs will join to the iron to make a covalent bond. What does it do? It transports oxygen. Okay, how does it transport oxygen? Well, you might be able to work it out because the heme group is a tetradentate ligand, tetra being 4. Okay, well, O2 acts as a ligand and comes on attaching here. So we can have oxygen getting attaching here as well, and then we end up with an octahedral complex. Yeah. But many of you may know that carbon monoxide, which is toxic and poisonous, interferes with that because it will stick to this and stick irreversibly to the iron. Okay, other examples, we have got copper phthalocyanin, which is used in dyes. It gives a nice bluish dye. We've got chlorophyll, so magnesium acts as a one there. Of course, magnesium is not a transition metal, but it's still, you know, undergoing sort of the idea of a ligand and a complex. So chlorophyll A gives a nice green color, and that is it for complex ions. It just needs you to do some practice of it. So good luck with your practice. Come back into class, and hopefully you'll be able to work through some questions. Thank you. Now let's end this Teams. Well, okay, you can see that's where we're adding them. I'll be adding this one in a minute, as long as I can turn the team off. So Teams window, meeting in general. Let's get that one. Okay, and now I can stop. And again.